I guess we can start. Hi everyone, my name is Vladimir Jovanović. Welcome to my talk. Today we'll be talking about Unicode and all the quirks that come with it. If you're not sure what Unicode is or how it works, that's okay. We'll talk about it later. But first, a bit about the company that sent me here. I am an Android developer at Superhuman, formerly known as Grammarly. We just announced our company rebrand this week, so it's a new way for me to introduce myself as well. Grammarly is the trusted AI assistant for communication and productivity. It seamlessly integrates with over 1 million applications and websites, helps over 40 million people brainstorm, compose, and enhance their communication. Most recently, Grammarly became part of Superhuman suite of apps and agents. The Superhuman suite includes 4 products. Grammarly's trusted writing partner that I already mentioned, Coda's all-in-one workspace, Mail's integrated inbox, and Superhuman Go, an AI assistant that brings proactive suggestions to users wherever they work. With that out of the way, story time. For legal reason, I must state that this story is not based on any product I worked on, and all similarities are purely coincidental. Let's say that you're working on an app and your product team decides to add public user profiles so that users can share content of the app. Designers create a simple screen like this one and you have to implement it. It's really simple. There is a profile picture and you can add a username. And yes, we need to limit usernames length to 30 characters because there should be a limit and 30 sounds like a good round number. Now when users start typing their username, we display the counter under the field similar to this one. Regarding the profile image, it would be too much of a hassle to allow users to upload whatever they want. We would need to screen and review images that are being uploaded. Because of that, we'll generate user profile image from their username, MVP style. If username is one word, we take the first letter of that word. If it's 2 or more words, we take the first letter of the first 2 words. Everything is excellent. You even decide to cover everything with tests and then you ship it. And it works amazingly. But then your product owner comes and says, we are a hip and modern company and we would like to allow users to add emojis to their usernames. And you're like, sure, no problem. You find this line and you remove this part. You try to run your code and everything goes sideways. Characters are not counted correctly, and image displays a dreaded question mark symbol. And then you realize that you will spend way more time learning about Unicode, Grapheme clusters, and emojis than you ever wanted. So for you to understand why this is happening, we'll need to go through a bit of history on how Unicode works and how emojis are implemented inside Unicode constraints. Let me start with a question. How many of you have ever seen these weird question marks or boxes where text should be? Okay, so a lot of you, but hopefully it's happening less and less. But that's what people lived before the advent of Unicode. According to Wikipedia, Unicode is a character encoding standard designed to support all of the world's writing system that can be digitized. And when I say all, I mean all. Version 17 defines 159,801 characters across 172 different scripts. We are talking about everything from Latin script that you're reading right now to Greek, Arabic, Chinese, Egyptian hieroglyphs, and even Klingon is included. But here's what's remarkable. Before Unicode existed, this level of global text support was basically impossible. Every system spoke its own digital language, and they couldn't talk to each other. Let me paint you a picture of what computing was like in 80s and early 90s. Every computer system had its character encoding, its way of turning bytes into letters. ASCII gave us up to 128 characters, great if you only wrote in English. ICO 8859-1 bumped it up to 256 characters, supporting most of the Western European languages. But if you need Japanese, you need Shift JIS. Chinese, GB 2312. Russian, KOI A-R. And here's the nightmare scenario. The same byte, let's say C4, could mean completely different things in different encoding systems. In ICO 8859-1, it's an uppercase letter A with umlaut, and in KOI 8-R, it's a Cyrillic lowercase letter D. Imagine trying to send an email from a computer in Russia to the one in Western Europe. Bytes would arrive perfectly, but the text would be complete gibberish. Troubleshooting these encoding issues was like being the digital detective. You would have to guess which encoding someone used just to be able to read the document correctly. Unicode solution was beautifully simple in concept. Give every character in every writing system a unique number. They call these numbers code points. So A is 0041, that's 65 in decimal. Greek letter omega, 03A9. Chinese character for middle, 4E2D. And that rocket emoji that we all love, that's 1F680. The U plus notation is just a standard way to write these code points, always with U plus and always in hexadecimal. The full range goes from 0000 all the way up to 10FFFF, which gives us over 1 million possible characters. However, here is the crucial insight that often trips up many people. A code point is simply an abstract number. It's like saying a concept of a letter A. To store that letter on a computer file or send it over the network, we need to turn that number into concrete bytes. And that's where things get interesting because Unicode gives us multiple ways to do so. Think of it this way. If Unicode code point is like an idea of a number, let's say 42, then UTF-8 and UTF-16 are like different ways of writing that number down. You could write 42 as decimal 42, as binary 42, as Roman numeral 42. Same number, different representations. UTF-8 and UTF-16 are both ways of encoding Unicode code points into bytes, but they use entirely different strategies. It's like having two different file formats for same data. They are both valid, both have their strengths and weaknesses, and choice depends on what you are trying to achieve or optimize for. And here's where a lot of confusion comes from. People think that UTF-8 and Unicode are the same thing, but Unicode is a character set, a big table that says 41 is a letter A, while UTF-8 is just one way of storing those characters as bytes. So UTF-8 uses anywhere from 1 to 4 bytes per character and has a clever self-synchronization system that I will explain later. But first, let me start by explaining why UTF-8 essentially dominated the internet. The killer feature is ASCII compatibility. Every ASCII character, English letter, common punctuation point, number, uses exactly 1 byte in UTF-8. And it's the exactly same byte that ASCII would use. So that means that any ASCII file is automatically a valid UTF-8 file, no conversion needed. This was huge for adoption. Web servers, databases, programming languages, everything that worked with ASCII would instantly work with UTF-8. You could upgrade gradually instead of having to rewrite everything at once. Okay. I mentioned that UTF-8 also has this property called self-synchronization. The first byte of a character has a unique bit pattern at the beginning that tells you how many bytes that character is stored in. And then continuation bytes start with 1, 0. So if you are thrown in the middle of UTF-8 stream and you see byte that starts with 1, 0, you know that you are in the middle of a character. So then you go backwards until you find a byte that doesn't start with 1, 0, and that's the beginning of your character. The numbers don't lie. Over 99% of all websites uses UTF-8. Today, it's a default for JSON, XML, HTML5, and most modern programming languages. So UTF-8 didn't just win the web, it is the web's text encoding standard. Let's talk about UTF-16, because whether you know it or not, it affects every Android app. Every string in your apps is stored as UTF-16. Most characters use 2 bytes, but some, like emojis, use 4 stored as something called surrogate pair. That's why the length of the rocket emoji is 2 and not 1, because it uses 2 UTF-16 units. This design comes from Java in the 90s when Unicode was smaller and 2 bytes seemed like enough. Java made this choice because in mid-90s, Unicode only defined characters in what's now called basic multilingual plane. Just 65,536 possible characters that fit perfectly into 16 bits. UTF-16 offered fixed-width encoding, which seemed ideal for performance and memory management at the time. UTF-8 existed, but was not yet dominant standard it is today. Android inherited this from Java by necessity. Changing string encoding would have broken Java compatibility and the entire ecosystem built around it. By the time Android launched in 2008, this decision was already locked in, and despite the thing that Unicode had grown far beyond the initial 65,536 characters. This is a great example on how early architectural decisions can have a lasting impact. What seemed like an optimal choice in '95 is creating complexity that we still have to deal with today. But cost of changing it across the whole Java ecosystem would just be enormous. Today, even though your strings are stored as UTF-16 in memory, almost everything else, like network, JSON requests, database, file I/O, uses UTF-8. So Android is constantly converting between UTF-8 and UTF-16 behind the scenes. You don't usually need to think about it, but it helps explain some odd behaviors. Let me show you how this plays out with real characters. A letter A, that's 1 byte in UTF-8, just like ASCII, and 2 bytes in UTF-16. So UTF-8 wins for English text when it comes to memory efficiency. Greek letter omega uses 2 bytes in UTF-8 and 2 bytes in UTF-16. So for most European languages, UTF-8 and UTF-16 are equal. Chinese character for middle uses 3 bytes in UTF-8 and only 2 bytes in UTF-16. So UTF-16 is more efficient here. It's more efficient only for some Chinese characters, not all of them. But here's where things get interesting. That rocket emoji, it takes 4 bytes in both encodings. That's because emojis live in what's called the astral planes, the areas beyond the basic multilingual plane, and both UTF-8 and UTF-16 need special handling for these characters. The key insight here is that there is no universally better encoding. It depends entirely on what languages you are working with and what your priorities are. If you're optimizing for backwards compatibility, then UTF-8 is perfect for you. If you're optimizing for consistent international text handling, then UTF-16 might be a better option. Okay. You may have heard me mention astral planes. That's not a sci-fi term. It's how Unicode refers to everything beyond the basic multilingual plane, which includes first 65,536 characters from 0000 all the way up to FFFF. Unicode divides its space into 17 planes, each with about the same number of possible characters. First one, plane 0, basic multilingual plane, or BMP. It contains most of the world's commonly used characters, Latin, Cyrillic, Arabic, Hebrew, and so on. Everything beyond that, plane 1 to 16, are called supplementary planes or astral planes. And they are not just for emojis. Plane 1 is for historic scripts like linear B or Egyptian hieroglyphs. Plane 2 is for rare or ancient Chinese, Japanese, and Korean characters. Emojis are mostly found in plane 1, but are also scattered in some other supplementary areas. And here's the key reason why this matters in your code. Any character outside of BMP, anything with a code point above FFFF, requires special handling. In UTF-16, you need to store it as a surrogate pairs, and it also takes 4 bytes in both UTF-8 and UTF-16. So when I say astral plane characters, I really mean any non-BMP character. They are more complex, they trip up indexing, and they are root of many bugs, especially on systems that are using UTF-16. Another peculiar thing about Unicode is that Unicode allows same text to be stored in different ways. Two of the most common are NFC and NFD. NFC, or normalization form composed, uses a single pre-composed character or code point when possible. In NFC, the letter E with an acute accent is stored as 00E9. NFD, or normalization form decomposed, stores the base letter and the accent separately. In the NFD, this E with an acute accent is stored as a normal E followed by combining acute accent. They look identical, but the underlying code points are different. This can break things in your app. A common example is sorting. These accented E's can be written in two ways. Without normalization, these might sort far apart in a list, even though they look identical. Searching can fail for the same reason. If your database stores things as NFD and then you search in NFC, result might come back empty even though the text appears to match. This is why many systems normalize text into a consistent form before storing or comparing it. To do it on Android, you can use android.icu.text.normalizer too. Now I'd like to show you something that will blow your mind and hopefully explain some bugs you have encountered. Look at this code. We have what appears to be a single family emoji, but when we call .length on it, we get 11. Not 1, not 2, 11. This is where Unicode gets wild. This family emoji isn't actually a single character. It's a composition of multiple characters held together by an invisible glue. So let me break it down. We start with an adult emoji. So it takes 2 UTF-16 units because it's in the astral plane. Then we have something called zero-width joiner, which is basically Unicode's way of stick the next thing to the previous thing. Then another adult emoji, a child emoji, joiner, then child emoji, then another joiner, another child emoji. And all this together is presented to user as a single family emoji. So what looks like one emoji to your users is actually 7 separate Unicode code points: adult joiner, child joiner, child. And that's why length returns 11 UTF-16 code units. This is called Grapheme cluster, multiple Unicode code points that combine to form what users perceives as a single character. And that's exactly the kind of thing that breaks assumptions in text processing. When you're counting characters for UI layout, validation, database storage, you need to be aware that what looks like a single character to your users might be many characters to your code. Let's take a look at a couple more types of hidden characters in Unicode: emoji modifiers and variation selectors. Emoji modifiers are used to change the appearance of base emoji. One common example is skin tone. For example, if we have dark skin thumbs up emoji, it's actually made of 2 Unicode code points: a base thumbs up emoji and dark skin tone modifier. Together they form a single visible emoji, but they are actually 2 Unicode code points. This is still Grapheme cluster and not a single character. But there's another subtle part of emoji rendering, and that's variation selectors. These are invisible code points that change how emoji is displayed to users. Let's take a heart symbol. That's 2764 in Unicode, just a heart symbol. Depending on the platform, it will be shown either as an emoji text emoji heart or text style heart. But we can force text style rendering by adding FE0E, or force emoji style rendering by adding FE0F. These selectors don't change the meaning of the character, only its appearance, but they are real code points that affect length emoji and emoji composition. So when you are slicing strings, validating username length, or generating initials, watch out for modifiers and variation selectors. They are invisible, but they count. To correctly count Grapheme clusters, we obviously cannot use .length or substring. The solution on Android is break iterator, using android.icu.text.breakIterator. There is also Java break iterator from java.txt, but it's not working as well as Android one. But luckily, they have the same API, so it's really easy to migrate from one to another. You just replace the import. Use case for counting the length of string in Grapheme clusters looks something like this. It's pretty simple. You initialize break iterator by calling getCharacter instance, then you iterate through the text. Well, you set text to it, then you iterate through it, and count how many times you can call next before you get to done. But before you go running off thinking I can just do this with regex instead, let me show you why this can be a trap, apart from regex being the maintenance trap. Dot in Java's regex matches a single UTF-16 code unit, not the full Grapheme cluster. This means that emoji Grapheme clusters will be split into matching components. Similarly, \w and \b are mostly ASCII-centric. They work fine for English text and letters and numbers, but they fail for letters with accent, non-Latin alphabets, and certainly for emojis. If you validate usernames, tokenized words, or sliced strings, using these defaults, you risk cutting characters in half or rejecting valid inputs. If you really want to use regex for some reason, you can use \x to match Grapheme clusters. This matches exactly one Grapheme cluster at a time and will never split emoji or combining sequence. When matching categories of characters, use Unicode properties instead of \w or things like that. For example, \pl matches a letter in any language, \pm matches combining marks, \pn matches numbers. So now that we know how to count Grapheme clusters and can fix our counter, let's fix the initials as well. To fix the profile image, we need to fetch not the first character of a word, but the first Grapheme cluster. This can be also done using break iterator. So, like this. It's also pretty simple. You initialize getCharacter instance, you set text to it, you call first to get the starting index, you call next to get the end index, and then you just take the substring from start till end. Now our input field is set. As you can see, length is calculated correctly and emojis are shown correctly in the profile image. But product owners don't sleep. They always think about new features that can introduce the strangest bugs to your code base. Things have progressed before this new request from the product owner. We now have a design system, and profile image is now in that design system maintained by another team. We also have a homepage feature where if users share something popular, they will be featured on the homepage with their name and their profile image. And then comes a simple request from the product owner. Please make the text in the profile image uppercase. Sure. 1 point ticket, one liner. Whatever getInitial function returns, we simply uppercase it. And done. I also updated a couple of tests because, of course, we have tests. We don't want to introduce some nasty bug to production. And everything is working great for weeks. And then things go bad, terrible. The app is crashing for everyone, everywhere on the homepage. Which line, what's the crash? Well, the crash is in our design system, in this line. And what's the crash log? Well, it says profile image cannot display more than 2 Grapheme clusters, SSH. What? How are we getting SSH? So I open the code base and start looking into the getInitials function. Yes, I split the username into words. I get the first Grapheme cluster at most 2 times. I put them together, and then I uppercase them. And then I get 3 Grapheme clusters. So it's the uppercase method. So I open the documentation for the uppercase method, and it says the length of the returned string can be different from the length of the original string. Did you know this? I didn't. So then, after some digging through the response on the homepage, we find this user. And at that point, I learned that the uppercase from sharp S is 2 letters S. And it's not the only character with that property. There are, for example, these Italian ligatures that some of them uppercase into 3 characters. To make things even weirder, from 2008, there is an uppercase sharp S in Unicode. And when lowercase, it gives you a lowercase sharp S, but for some reason, not vice versa. Greek letter sigma, lowercase, gives you this Greek letter sigma. But there are 2 lowercase Greek sigmas. And when uppercase, they give you the same uppercase sigma. The Italian long S, from which we derive the symbol for integral, lowercase becomes regular S. So be careful with uppercase and lowercase methods. Uppercasing and then lowercasing something won't necessarily produce the same string that you started with. Zalgo text can also create some weird things in your input fields. Just search for it. And you will see how far you can get by abusing what Unicode offers. And there are many more weird things with Chinese, Egyptian, Klingon, Elvish, and all the other writing systems that humanity created. If you want to be cool and enable Elvish for your users, make sure to have fonts that support it, make sure to test everything, and then test it a bit more. Things can fail in unexpected ways. We solve the issue by simply not uppercasing the letters that change length when uppercased. But even if you introduce a Unicode bug, don't worry too much. Learn from it, it happens to the best of us. A few years back, a sequence of emojis, a white flag, a 0, and a rainbow with variation selector crushed iPhones when the text renderer could not handle it. Apps like iMessages would just close instantly. On Android, something similar happened. A message with a black dot emoji caused WhatsApp and some other messaging apps to crash when the dot was tapped. It looked harmless, but it contained thousands of invisible characters that broke layout logic. Tom Scott even made a video about it. If you want to learn more, you can check it out. So if people building operating systems can get caught by this complexity, we are in good company. Unicode can be tricky, but it's also what makes it fun. The more you know, the fewer surprises it will throw your way. And that's everything from me. Thank you. So thank you again for listening to this talk and to this hypothetical story that never happened. I hope you learned something today. If you have any questions, you can ask them now. Here are my contact details. I will share slides on Blue Sky. And if you would like to relocate to Berlin and join Grammarly or Superhuman, please reach out to me on LinkedIn and I will send your contacts to HR. That's it from me. Questions?
What's your favorite Unicode character?
Today, this one. Okay, thank you again. Yeah, please.
But, do you know anything about the security complications from this? Do you have any story or idea about it?
Some weird things can happen. I was talking with people from a different company, and which problem they had. Like, there was an input field, and if something goes wrong, they take the first 100 characters of the input field and just put it in like log message together with like exception and send it to their backend. And occasionally that JSON would just not be well formatted. It would just fail to parse. So they were checking what's happening, and closing quotation was not there. So there would be like user input field, then like no quotation, and then just rest of JSON. So and they were trying to figure out what's happening. So basically, if your 100th character is an emoji, and you cut it in half, so it's not like end of emoji, just like middle of it, then your last Unicode code is zero-width joiner. And that thing just glues the closing quotation mark to the emoji, so it just disappears. So there's not really that much security implication, but there are some weird things that can happen that it's really hard to debug it. So I would always suggest just trimming or using break iterator to actually grab the whole like characters in a text.
Because if you think about it, just an idea, a character crashing an application, that's a denial of service.
Yeah.
So that's why I asked.
Well, yes. Also, like the black dot just crashed all the apps. And what it did, it has like thousands of different characters that are all switching from left to right and right to left. So when you click on it, system tries to decide like where you clicked actually, because it thinks it's much longer, and it just gets confused by like all the reversal of or like direction, and it just crashed. So can do some weird things with it. Okay, thank you.